In this video, we're going to go ahead and discuss curve sketching for a periodic function, or in this case, a trig function. And we'll just take a look and see what some of the behaviors are. So we notice that we have an x out front. That's going to kind of complicate matters just a bit, but not too much. So one of the things we want to try to find are intercepts, what the behavior is like at infinity, and because of the periodic behavior of tangent, that's going to be awful tough. And so at infinity, we're not going to concentrate so much at infinity as we are just in a localized area. And that localized area is going to be centered around 0 because that's where when x is 0, then we start having differences in that. And so we also want to determine any points of indeterminacy or any points of undefined behavior. So let's go ahead and look at the undefined behavior first. If we take a look at tangent of x and rewrite it as sine of x over cosine of x, then cosine of x equals 0 implies that x is equal to some odd number times pi over 2. This means like 1 pi over 2, or 3 pi over 2, or negative 1 pi over 2, or negative 3 pi over 2, that sort of thing. Because that's when cosine is 0 whenever you're at 90 or 270. Okay, so now these are all of our vertical asymptotes when x is equal to an odd number times pi all over 2. Okay, so now we've already talked about behavior at infinity. It's not going to play a part in this because we've got some interesting behavior around 0. And so after that, it just takes longer and longer to run through the cycle, is what it amounts to. So now we're looking at, is it possible to have an indeterminate form? So is it possible for sine and cosine to be 0 at the same time? And no, it's not. They can be the same value at the same time, which is that occurs at multiples of 45 degrees, but or the oddball multiples of 45 degrees. But they can't both be 0 at the same time, which is good. So now we've found that out. Are there any intercepts? Okay, and so we look at when is f of x equal to 0. So 0 equals x tangent x. Now this occurs wherever x equals 0 or sine of x equals 0, but they both occur at x equals 0. Okay, sine occurs at, so that's one of them. Sine is 0 at x is equal to 0 or pi or 2 pi or negative pi or negative 2 pi. All right, and so if we just take a look at within a few vertical asymptotes, we're pretty much going to be looking at negative pi and pi. Okay, so that means that we have zeros there, and now do we have any points where when x is 0? Well, when x is 0, y is 0, and so we are going to pass through the point 0, 0. That's going to be our only x-intercept. At least until sine is 0, and we've already talked about that. That's our y-intercept. So our only y-intercept. I apologize. This is not an x-intercept. This is our only y-intercept. When x is 0, we're talking about the y-intercept. Man, it's just been a rough day for algebra. But so when x is 0, that makes everything else 0, and so it only occurs at one point, and that's where y is 0. Now, let's go ahead and make a list because I'm already losing track. We have vertical asymptotes, and this is that x is equal to negative 3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. We have a y-intercept at 0, 0. We have x-intercepts at pi over 2, well, negative pi 0, 0, 0, and pi 0. And that looks like that's it. So here's a listing of all the things that we have so far. Now let's go ahead and take a look at that first derivative so we can find any extrema, if there are any. And so we take our first derivative of the first, now this is product rule, so derivative of the first times the second, so that's just tangent x, plus the derivative of the second times the first, and that's secant x secant squared x. Okay, so now we can find any points where this is 0 or does not exist, and well, we have critical points, but they're only wherever cosine is 0, and so that's going to be the same problem with our vertical asymptotes. So now we have to find out, well, when is it 0? Okay, so we have 0 is equal to, and this is a sine over cosine matter again, plus x over, and now this is cosine squared x. So now if we were to go ahead and throw this in here, we'd say, oh, okay, well, that's true whenever sine x and x are the same, which is 0. So when x is 0, this is true. And then we have to say, okay, when does sine x ever equal negative x? It doesn't. It doesn't ever equal it again. And so that's it. So we have at 0, x equals 0, which means at the point 0, 0, we have a critical point. Now, does that mean that it's relative min or max? Well, let's go ahead and test that. And we do that through our second derivative test. So our second derivative is derivative of the first is secant squared x plus the derivative of the first times the second plus the derivative of the second, which is 2 secant x times the derivative of what's inside, which is secant tangent. Okay, times the first, which was x. So now if we clean this up just a little bit, I'm going to factor out secant squared x. And now that means that I've got 1 plus 1 is 2 plus 2x tangent x. Now, we want to find out what the value of this, or what the sign of this is at 0, at x equals 0. Well, at x equals 0, this becomes 1. This becomes 1. This becomes 0, and so we're just left with 1 times 2 is 2, and so this is greater than 0. So it's concave up. So now we have our vertical asymptotes, we have our y-intercept, we have our x-intercepts, we have our critical points, and we have our concavity at those critical points. So one other behavior we want to look at is when x is negative, because we have again, we have that cyclical kind of thing, and so we have to be very cautious here. Okay, so let's go ahead and draw out my big things here. Now I've got my pi over 2. This is pi. This is 3 pi over 2. And now I go backwards the other way, and I've got negative pi over 2. I've got pi, negative pi, and negative 3 pi over 2. Okay, and so let's go ahead and put in our vertical asymptotes. And we had vertical asymptotes at the odd numbers. And so I'm going to go ahead and throw in my vertical asymptotes. Whoop, oh, that's getting kind of curvish. Okay. All right, and now we have concave up. We have this. At the point 0, 0, we have a critical point, and it's concave up at that point. And so this is going to be asymptotic. It's going to look like that because it's all concave up. And now let's look at the behavior on either side of this. So when we hit as we're coming, as we're approaching the limit as pi over 2, take a look at the original function, which was x tangent. Okay, this is positive here, but as we approach pi over 2 from pi, okay, that means that cosine is going to be negative, but sine is positive, so that whole mess is negative. Okay, so coming up here, that whole mess is going to be negative, and then it passes through pi. And now it says again, well, what happens after that? Well, once we hit pi, then we've got both cosine and sine negative, and we've got x is positive, so we have a net positive look. And so it really does start looking like tangent. On the other side, as we approach negative pi, so now keep this in mind here, this is actually 270 degrees. And so now we're back down in that third quadrant, but x is negative, and so that's going to drive it negative. And now when we come back the other way, we'll notice that we're back in that second quadrant, which is negative, but x is negative as well, making the whole mess a positive. And so this is what it's going to look like. Okay, so we've got sine is negative. We've got x is negative, and we've got cosine positive. Okay, that's why we get a positive outflow. Here we've got sine, cosine, and x all negative. So 1, 2, 3, 3 negatives make up a negative. Here we've got x and sine are positive, cosine is negative. And here we've got all 3 positive. And that's how we determine that behavior. These are supposed to be mirror images of each other, by the way, but I got a little crazy over here. This should probably come over more like that. All right, that's curve sketching for trig functions. It's not that bad.